This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. Carta brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
I am, in fact, literally the bridge between the past and the future in many different ways. And so this is the title that I originally chose when I submitted my first abstract. But as I got to preparing it, I thought I would try something new with the same material that I've been working on for some time. So I've rechanged the name now, Anatomy of a Climate Regime Change. And it's the same material, basically, but the hypothesis is that we may be, with our modern instrumentation, over the last 20 or so years, we may be seeing a change in climate that is something like those that might have caused Jeff Severinghouse's abrupt transitions. And I'm going to go through it with you. It is, of course, a very small version of very big events that happened in the past. So I first got interested in this problem because of an issue of public awareness and policy. The public issue is called the paradox, the hiatus paradox. You can, if you cherry pick your data, as this article did, you can find a time in 1997, another time in 2012 when the Earth's temperature was the same that it had been. And this led to the idea that the globe is not warming, even though the carbon dioxide is increasing. So I began to ask myself two other questions. What else was going on while the global temperature was constant? Was climate change also disappearing? And I found, of course, two other paradoxes. Why are the extreme events in climate increasing? And here's the key issue. Why is the Arctic warming even more rapidly? So let's first of all verify that this is the hiatus. It started in the year 2000. And during that time, the carbon dioxide has increased, and humans have added about 27% more CO2 than they have since the beginning of the Industrial Revolution. And this should have led to an increase in the warming rate in climatologist language of 0.4 of a watt per meter. So we were putting more energy into the climate, but it wasn't turning up in the global temperature. And the question was, where was that energy going? So here's a longer perspective on the hiatus. This is a record since 1880, and it shows the much shorter record than you've seen thus far, but it shows the global temperature evolution. And the first thing you notice is that there was another hiatus about between 45 and 75. They do happen. They are features of climate models. They are areas where the climate goes through a reconfiguration. Our present hiatus started with a bang, with a huge El Nino in 1997 and 8, my first year as director of Scripps, when my office was inundated. And then you can see the profile of the slowing warming that we've seen throughout this century. Now, the global mean temperature that the scientists calculate is taken from data, and most of it is from satellite observations of the sea surface temperature, and the sea covers 70% of the Earth's surface, so you would expect that this computation will be dominated by what's happening in the ocean. And after many gyrations, the community came to realize that it was the ocean, it's the behavior of the ocean that was responsible for this hiatus in warming, because we knew from earlier studies going back to the 1980s that Pacific Ocean, for example, could oscillate between two very extreme states in which the temperature changes dramatically. And you'll notice that El Nino is a warm state and La Nina is a cool state, and so perhaps what was happening was that we were switching from El Nino to La Nina, a prevailing state thereof. So I have to tell you a little bit, just a little bit, about how the El Nino cycle works. So what you're looking at here is a picture taken from the sketch taken from the Pacific equator, stretching from the east in Lima to the west in Darwin. And you'll see at the top in the La Nina phase, the trade winds push the wavy ocean towards the west. And that water heats up from the sun as it goes, and as it heats up, it expands a little bit, so the winds have to push the water upstream, uphill, and it goes until it can't go any further, and so you get a deep water in the western Pacific that's warm, and then this circulation pattern pushes up cold water in the east, and that's the cooling phase of the La Nina. The El Nino is a little bit different. The trade winds can suddenly stop for some reason, and then all this water rushes downhill, and the warm water gets heated a second time as it crosses the Pacific, and you slosh up against the North American and South American continents. So what happened? Did the trade winds increase? And were of the right sense to create an El Nino, a La Nina? And the answer is, from this remarkably difficult data set to compile, 100 years of the trade wind stress on the ocean water in the central Pacific. And you can see it oscillated around until about the year 2000, when it switched from El Nino sense, smaller trade wind, to La Nina sense, larger trade wind. It's continuing to get larger in the negative direction. That's the negative part of this curve, and it's unprecedentedly large, and it is not included at present in contemporary climate models. But the trade wind has been exceptionally large, which means then you would think, if that were the case, that in fact you were driving a lot of heat energy into the ocean in the western Pacific. So here is a picture of ocean heat content that was published just about 6 or 7 months ago in Science, but it looks like it solves the problem. And what Chen and Tang did was divide their time that they looked at the data from before the hiatus on the right and after the hiatus began on the left. And you see two plots. The bottom one is the one pertinent to my argument about the El Nino, and I'll come to the top one in a moment. What you see is a spread against longitude across the Pacific. The red blob is the distribution of ocean heat down to about 300 meters, and you see this abrupt switch in colors, if you will, the same switch that you saw in that earlier picture from Woods Hole. So what we do know is that at around the time of the hiatus, the Pacific Ocean state changed to a heat sequestering state. But the other thing that happened, which actually took over after a while during this same period, was this is displayed in this plot on the left, which is somewhat different because it's a transect up the Atlantic from south to north, and it shows you where in the new heat is being buried in the North Atlantic. And you can see basically that the heat is being buried at pretty high latitudes. And this started at approximately the same time. And this little event here that we are observing is a small version of the events that Jeff Severinghaus was talking about somewhat earlier, where it was possible to slow down the Atlantic meridian circulation. And you can see the strong difference between the two states. And this change took place across the large El Nino that started the process off. So what else was going on during this time? The oceans would tell you this spread all around the Earth, all around the Earth's ocean, and that tells you right away that we're dealing with a comprehensive change in ocean state. And you would expect then that there would be other changes in the climate that occurred at the same time, other parts of this restructuring. And as you probably have understood from the pictures of polar bears, there actually is an Arctic regime shift in progress. And this was first revealed by two formal assessments, one in 2005 that used primarily data from before the hiatus began, and another one only 7 years later, and they discovered a major change in the distribution of Arctic heating. During the hiatus, it's been fastest in spring and autumn, and before it was fastest in winter, which was consistent with the earlier greenhouse warming models. It's now faster over the oceans than the land. So these change in patterns suggested to you that the Arctic was developed a new warming source that was not as strong in the previous period. So this is satellite data first began to be collected with greatly accurate data on sea ice area in '79. And here is the curve that you can see of the minimum sea ice extent, which occurs at the end of the warm season in September, as a function of time, September after September, since 1979. And what you can infer from this plot is a break in behavior in which the sea ice was slowly declining, but oscillating about a slowly declining mean, and suddenly there looks like a change in state. And over this period of time, the sea ice area has declined by about 40%, and the sea ice volume is down to 25% what it had been in 1979. So here's the same data, and that was there in case the movie didn't work. That shows you where the timing of the sea ice decline. And there's one other thing that has happened during the period of the hiatus, which I think will be interesting to Jeff and others. It's a small analog of the events that slow the meridional overturning circulation. During this hiatus, and only since about the year 2000, a new pattern of winds developed over the Arctic Ocean. It's called the Arctic dipolar anomaly, and this pair of winds going in opposite directions drives ice and sea and fresh water from the Arctic into the North Atlantic, where it will shut off, or it can impede, where it collides basically with the Gulf Stream, and at that collision point, the water sinks to depth, and we did see that. Now, this is a small event of something that actually happened in the historical record 8,000 years ago as the ice sheet was retreating across North America. As it retreated, it left behind in the area of Hudson Bay a huge glacial lake that was contained between the melting ice on the one hand and the moraine that had pushed up on the front. These glacial moraines are unstable, and there was a huge outflow of water that occurred all at once. and there was a 200-year period of cool climate that then recovered. The Columbia River was also formed this way, and what the satellites have observed is a great injection of fresh water into this gyre here, the Beaufort Gyre, that began at approximately the same time, and that water is lighter, and when it gets to the saltier Atlantic will sink. So here's the next and the most important point. This sea ice retreat that I just documented is warming the Arctic by a very simple mechanism. When you replace white ice with blue ocean, you absorb much more solar energy. The sea ice itself may reflect half back to space, and the ocean absorbs 93% of the energy that's falling on it. So as the sea ice retreats, it warms the Arctic. And a recent paper that came out from Scripps measured the degree of warming since the satellite era started in '79, and they found that the net sea ice retreat adds about 6 watts per meter squared, but 2/3 of the heating that took place in that period occurred in the 10 years between '01 and '11. And the Arctic is small, but if you average this over the globe, you get 0.21 watts per meter squared, which is about a quarter of the increase that you would have expected from the increase in greenhouse gas at that time. So you have added a new warming mechanism that the climate, at least in recent times, was not used to. So the question before, this is a picture of the geography of heat transport in the climate. And I put it on, even though it's complicated, just to remind you that the basic circulation of the atmosphere, as understood from the time of Edmund Halley, was there was heavy and strong warming of the ocean and land over the tropics. This heat was then transported to the north. So it was a north-south circulation, north equator to pole circulation that is the fundamental feature of our climate transport. If you suddenly add a new heating source at the poles, particularly the Arctic, won't you change the circulation of heat in the atmosphere? And will this not, in fact, lead to states like the El Nino? So what we do know, and this is a question still under active investigation, but what we do know is that we have created a 17 or 18-year persistent La Nina-like state in the Pacific Ocean, and also a similar outflow in the North Atlantic, that is lasting longer than most typical La Ninas. It lasted the whole period of time. And what this has had an effect on the climate down below, because when you're in a La Nina state, you bend the jet stream, as you see, and you've seen many, many pictures recently. Anytime you look at the weather, you'll see the jet stream dipping deep into central United States. So we've remained in a state of jet stream, La Nina-like jet stream. And the weather patterns then correlate with this. Now the question is, the global temperature has been constant, so you would expect then that there would be very many fewer heat waves, right? Or at least the same number as before. This has not proven the case. Here's a remarkable data analysis generated in Spain, where they were able to compile the mean summer temperature in Europe for the last 500 years, since 1500. And what you see is 5 of the 10 years in the 2010 were the hottest years, in the 2010 decade, were the hottest years on record. You also hear about this you hear this bending La Nina-like jet stream. You hear about it in another context, because in the winter, it brings Arctic air to the south and has been responsible for the large snowstorms that we've seen in the past. We also know that the La Nina state implies a very dry climate in California, something that we are presently observing. So here are the questions. I phrased hypothesis at a set of questions. Did the Arctic warming associated with the Super El Nino, which pushed the ice over the edge, did it trigger a continuing ice retreat when winter regrowth could not make up for the previous year's loss? Did Arctic warming, by altering the north-south heat flow, did it strengthen the trade winds, create the La Nina bias, and enable the persistent ocean heat sequestration that we've been seeing? Did it, warming, by altering the heat flow, cause the observed pattern and enhancement of extreme event occurrence? And then finally, how long can this kind of thing go on? Will the present dynamical quasi-equilibrium be maintained until the energy added to the climate system from ice and snow retreat stops? No, thank you.